Hello everyone. Sorry, the video was cut out in the previous video that I was recording. So we were trying to introduce the concept of thermal energy reservoirs, and the first thing we needed to know is basically what is the concept of thermal energy reservoir. So thermal energy reservoir is a reservoir which has very high thermal energy capacity. So thermal energy capacity, usually it's shown with capital C, and you can write it in terms of mass multiplied by specific heat of that specific fluid that you're talking about. So it should have either a very large mass or a very large value of specific heat. So examples of thermal energy capacities are, lakes, ocean, atmospheric air. So the reason that we call them thermal energy reservoir is that, for example, let's go back to that example of the hot coffee. So if you put the hot coffee in the room and the temperature of that hot coffee drops to the room temperature, what happens to the room temperature? Probably your room temperature doesn't change, right? Because the heat that it is received from that hot coffee is not really changing the whole temperature of the room. So that's why that room or that atmospheric air around the hot coffee is considered to be a thermal energy reservoir. So with that, we want to start talking about the engineering devices. The first one is the heat engine. So if you look at this picture on the bottom right, you see that there is a paddle wheel working. A work is applied to this, it rotates, and the work is converted to the heat, right, directly, no problem. But now consider the same system and you add heat to that water. Do you think that paddle will start to rotate? No, right? It has a certain direction, right? In order to do this, in order to convert this heat to a work, you need to have some special devices, and that device is called heat engine. So heat engine is a device that converts heat to work. Okay, so how does it work? It receives heat from a high temperature source. So high temperature source is a thermal energy reservoir which has high temperature, so we call it source. Okay, so source of heat. So it receives the heat from that into that heat engine, right? And it produces some work. We will talk about this later. But it produces some work, and then it loses some heat to a low temperature sink. So low temperature sink is a thermal reservoir which receives heat, so it has a low temperature. Okay, so usually these heat engines, these devices have working fluid, and the working fluid is a fluid that basically moves and receive heat. For example, let's say you have water, right? It receives heat from the high temperature source, and it produces some work in the heat engine, and then the temperature of that is dropped. It goes to a low sink temperature, and this water cycle through the system. So these processes are cyclic. Okay, it means that you have a working fluid that goes through all the processes and goes back again to the same point. So an example of these heat engines are a steam power plant. So if you look at this steam power plant, you see that there is a boiler, and the boiler receives the heat from a high energy source or a source such as a furnace, right? And that steam goes with high temperature to a turbine. Turbine produces some work out, and then the temperature of that steam drops. After producing some work, it goes to a condenser. Condenser loses heat into an energy sink such as a lake or such as atmosphere, or whatever that is. It goes back to a pump. Basically increase the pressure of the fluid or the water to the temperature required by the boiler. So it's a cycle. So the water goes through this cycle, and there's a work input to the pump that you need to produce work, right? So there's a work input, there's a work output here, there's a heat output to the energy sink, and there is a heat input from the energy source, right? So this is a cycle. Now, if you want to write the first law of thermodynamics for this system, what do you write? So remember the cycles. The cycles, one of the important properties of the cycles were that delta U was equal to 0. So the internal energy change is 0. So the first law of thermodynamics says that delta E is equal to delta U plus delta kinetic energy plus delta potential energy. So this system, the potential energy and kinetic energy is negligible, and delta U is also 0 because it's a cycle. So delta E is equal to 0, and delta E is the difference between work and heat, the net work and the net heat, right? So therefore, since delta E is equal to 0, then the net work out is equal to the net heat in, right? So the net work out is equal to W out minus W in, the work output minus work input, and the net heat in is basically equal to Q in minus Q out. So these two are equal to each other, right? So you can say that the total work, the net output work, is equal to the difference between the heat of your system. Now, one important point is that your system boundary is the whole system, right? So if you only consider the turbine, that turbine is an open system because mass is coming out in, mass is leaving your system, right? And you need to write the first law of thermodynamics for this specific system, and that's an open system. However, if you consider the whole system, and the boiler, the turbine, the condenser, the pump as one single system, then there is no mass transfer, and that's a closed system. So in this closed system, you have again those heat input, heat output, work input, right? So you can write the first law of thermodynamics for that system based on a closed system type of equations, right? All right, so that's the idea, right? And you can see it in this picture. Sometimes we show it with high temperature reservoir. That's again the same. That's the source, goes to the heat engine. There is a work output and there is a heat output. So we usually show that heat that is coming from high temperature with QH, and we show the heat that is going into the low temperature source as QL, and WNet is out, right? So remember the definition of the efficiency. Efficiency was the desired output divided by required input, right? So the desired output in this case, what do we want from a heat engine? We want to produce some work, right? So that work, net work output, is our desired output. And what do we input into the system? We have some heat coming into the system, right? So that's the total heat input to the system is considered to be the required input, right? So that's the definition of efficiency. And we mentioned that WNet from the previous slide. WNet is equal to Q in minus Q out. And if you substitute that, you get into this equation. Substitute Q out with QL and Q in by QH, you get to this equation. Sometimes we write it this way. Okay, so that's the efficiency of the heat engines. All right, so that's the same equation. In the next video, I'm gonna do an example on the efficiency of the heat engines.